The .NET libraries have a mechanism built in to help us generate cryptographically secure random numbers. We'll be using the random number generator class to generate our random numbers, so let's take a look at a demo of how to use the random number generator class. Now what we're going to do in this simple example is using the random number generator class in system.security.cryptography, we're going to call the getBytes method, and we're going to generate a random number. Now you'll see that we're passing 32 into getBytes. So that's saying that we want to return 32 bytes of random data, or in this case, that's 256 bits. You can pass anything you want into this. If you only want 16 bytes, then you can pass in 16. But for this example, we're going to pass in 32. Then what we do is we want to display the random number that's been generated into our window here, so into these little text boxes. Now before we can do that, if you want to just return the byte array itself, it'll just display like a bunch of weird characters and letters and numbers onto the screen. And that's not very human readable. So what you want to do is you want to convert it into a format that is more easily readable. And what we're going to do is we're going to convert it into what's called a base 64 string. So as you can see here, we have convert dot to base 64 string. That takes a random number and then outputs a string. Now base 64 strings are designed to be human readable. So if you ever wanted to store a random number in, say, a database, converting it to a base 64 string first is a good practice. Now it's important to understand that base 64 encoding is not encryption. That's very important. It's an encoding format. So you're just changing one format from a byte array into something that's more readable. So it's not encryption. And so a lot of people get confused with the difference between encoding and encryption, and encoding is definitely not encryption. Okay, so let's run this project and see what happens. First of all, we're going to generate our first random number by calling getBytes. Now if we look down here into the autos, we could see that we now have 32 bytes of random numbers. So if we take a look here, these are our random numbers, our 32 bytes of random numbers that we've just generated. So then we want to write those to the window. So now we've gone through all 10 iterations. So now you'll notice that each of those strings looks completely different. So there's no kind of replication or duplication in any of these numbers. They're all completely random. And this is a very important property in cryptography because we want truly random numbers to become our encryption keys. And this is something we're going to explore later. But for now, we've covered a very simple and very important topic, and that is generating a pure, cryptographically secure random number. And as we've seen, it just takes one line of code to do it. Now this is going to become a common theme throughout this video, because sometimes cryptography can appear rather daunting to a new developer. Now, if we start looking into how these algorithms are actually implemented, how people come up with them, then yes, it's very complicated. But as a practicing software developer, as someone who just wants to use this stuff to build systems, then actually it's not very hard to use. So the APIs that are provided by Microsoft within .NET make these encryption algorithms and tools very straightforward to use. In this demo, we're going to look at using AES to encrypt and decrypt some data. I'll demonstrate how to generate your encryption key as a large random number, which in this case will be a 256-bit key. I'll also do the same for the initialization vector, which is 128 bits or 16 bytes in length. And here we have two methods. We have encrypt and decrypt. Thankfully, using the AES class to encrypt and decrypt data is very straightforward. It's only a few lines of code. So for our encrypt method, we take a byte array of our data to encrypt. So if you were encrypting a string, you would first need to convert it to a byte array. We have a byte array for a key, which in this case will be 32 bytes or 256 bits. And we have a byte array for our initialization vector. So to encrypt some data with AES, first of all, we call the static create method on the AES class, which gives us our instance of the AES encryptor. We then assign the key to the key property. Then to encrypt with cipher block chaining, we simply call encrypt CBC, and we pass in our data to encrypt and our initialization vector. Then that will return us a byte array, which will be our encrypted data. To decrypt some data, we call our decrypt method, and in here we pass in a byte array of our data to decrypt. We pass in the byte array of our key, the same key that we use to encrypt, and we pass in the initialization vector. Again, the same initialization vector we used as part of the encryption process. The decryption is very simple. So we call the static create method on the AES class. We then assign our key to the key property, and then simply we just call decrypt CBC whilst passing in our data to decrypt and the initialization vector. In our method here called AES CBC, we have a message from user input. We have a key which we generate using the random number generator class, where we call get bytes and pass in 32. We have our initialization vector, and then simply we call our encrypt method. First of all, we take our string that we want to encrypt and we call encoding.utf8.getBytes to convert it into a byte array, and we pass in our key and initialization vector, and then straight away we decrypt that message, which gives us back a byte array. Now we want to display that byte array onto the screen, so we need to convert it into something that's more readable. So in this case, we just call encoding.utf8.getString, and we can just convert that to a string. Okay, so now let's run it and see how it looks. I'll type in a message to encrypt here, so I'll just put a super secret message. So I'm just going to step into our method, and we're going to generate our key and initialization vector. So as you can see here, here's our key, and here is our initialization vector. And then we call that encrypt method that we looked at earlier, and that gives us a byte array of our encrypted data, which we can see here. So that's our encrypted data, and we can decrypt it straight away, which again gives us a byte array of the encrypted data. So we're converting that to a string, and then down here you could see the string says super secret message, which is exactly the same as our original string. We can reflect that onto the screen. So we've got our original message, we have what it looks like once it was encrypted, and then we could see the result once we've decrypted that data. As you can see, using AES is very straightforward. The actual encryption and decryption is just a few lines of code. Now let's take some data to encrypt and decrypt it using the AES GCM mode. We'll need to generate a key as well as a 12-byte nonce value that is passed into the encryption algorithm. We have two methods, encrypt and decrypt, and these are coded to use AES GCM. So let's take a look at encrypt first. So the encrypt method is going to take a byte array, which is our data to encrypt, just like we saw previously. We also have a byte array for our key, a byte array for our nonce, which is 12 bytes instead of 16. Effectively, it's like an initialization vector. And we also have a byte array for our associated data, which is arbitrary metadata that you can pass in along with your data to be encrypted. This method then returns a tuple of information, 2 byte arrays. The first byte array is our ciphertext, so that's the encrypted data, and the second byte array is our tag, which is effectively like an HMAC, which has been generated as part of the encryption process. So first of all in this method, we pre-initialize a 16-byte byte array, which is going to store our tag after the encryption process. Then we pre-initialize a byte array for our data to encrypt, and then we pre-compute that to the length of the original data that we're encrypting. Then what we do is we create an instance of the AES GCM class, and we pass in our encryption key into the constructor. Then we simply call AES GCM.encrypt, and we pass in our nonce, our data to encrypt, the ciphertext pre-initialized array, the pre-initialized tag, and our associated data. And then we return that tuple. Decrypting data is pretty much just as straightforward. So we have our decrypt method, and we pass in a byte array of our ciphertext. We pass in a byte array of our key, the same key that we used to encrypt with, a byte array for our nonce. We pass in the tag that was returned from the encrypt method, and we pass in a byte array of our associated data. And this method will return a simple byte array, which will be our decrypted data. So here we pre-initialize a byte array to store our decrypted data. We create a new instance of the AES GCM class, and we again pass in our key. Then we call decrypt, and we pass in the nonce, the ciphertext, the tag, the decrypted data, and the associated data. And that will give us our decrypted data that we can return. It's fairly straightforward, so it's a little more complicated than the cipher block chaining version of AES that we just used earlier, but not much more. So if we look into our AES GCM method, we have a string that we're going to encrypt, and we create our key, which is 32 bytes that we created with the random number generator class. We have our nonce, which is 12 bytes, and then we encrypt some data. We're taking our original data that the user passes in, and we're converting it to a byte array first because it originates as a string. For the metadata that we're passing through, we're just passing in a string that says arbitrary metadata, which again, we have to convert into a byte array. Once we've encrypted that data, we then decrypt it straight away by passing in the ciphertext, the key, the nonce, tag, and then we reflect that onto the screen. So let's enter in a message to encrypt. Super secret message, encrypt. So let's step into this. We create our key. We create our nonce. So our key is 32 bytes, and our nonce is 12. As we go into the encryption method, we have our data to encrypt, which is a byte array of 20 bytes, a key, which is 32 bytes, the nonce, which is 12 bytes, and the associated data, which is 18 bytes. We initialize the tag, initialize a byte array for our ciphertext, instantiate the AES GCM class, we run our encrypt method, and here we have the ciphertext, which is a byte array, and our tag. And then what we can do is we can decrypt that straight away. We pre-compute a byte array for our decrypted data. We create the AES GCM class by passing in the key. We call our decrypt method, and then this byte array contains our decrypted data. So then we can go and reflect this onto the screen. So we're turning our ciphertext into a base 64 string. In the window we can see the results. So we've got our original text, our encrypted text, and our decrypted text, which reads as super secret message. So let's run this again, but without any breakpoints. So I'll enter in a message to encrypt, and then it'll encrypt it with AES CBC, and then with AES GCM, and then it'll return our decrypted text. So I'll enter in super secret. I'll encrypt it, and you can see it encrypted with AES CBC, and here it is, and it encrypted with AES GCM, and here's our decrypted text for both, and it's the same. GCM ciphers are the most widely used ciphers in the world today. With GCM mode, most implementations perform the authentication check on the Mac and the encryption in parallel, and this makes GCM a high-performance implementation of the algorithm. If you're in a position to use GCM in your software, then I think you definitely should. In this demo, I'll show you how the data protection class works, and I'll show you how to use this with AES GCM. So we'll use the AES GCM encryption just like we did in the previous example, but then we're going to use the Protected Data API to protect that AES key. So let's look at some of the helpers that we have here. So we have our GCM helper class, which is exactly the same as what we looked at in the last demo. We have an encrypt and decrypt method that takes our data to encrypt, our key, our nonce, and associated data. It will encrypt that to return a tuple with the ciphertext in the tag. Then we have our decrypt method, which takes our ciphertext as a byte array, the key, the nonce, the tag, and the associated data, and it will then decrypt that data and return it back to us. So it's exactly the same as what we looked at previously. Now we have a helper class here called protectedhelper.cs with some methods inside. Now the protected data class is only supported on Windows, not Mac or Linux. So if we want to encrypt something using the data protection API, we pass in a byte array of what we want to encrypt, we pass in some optional entropy, and we pass in the data protection scope. Now the optional entropy is a bit like the initialization vector. So what this means is that every time you go to encrypt some data, you generate some new entropy. So if I have a message and I encrypt that using the data protection API, and then I encrypt it again, then the ciphertext will look the same. But by providing some additional entropy, it just basically means that we can avoid having repetitive sequences of bytes in our ciphertext. And this is pretty handy. We then have the data protection scope. This means that we can protect our data either as a local user or at the current machine level. So here we have a method for our button click. And what we're doing here, on the first half of this method, we're going to create some data using AES GCM identical to what we looked at previously. Then we're going to take that key we generated for the AES GCM example, and then we're going to protect it using the data protection API. So what we're going to do here, and we're going to step through this in a moment, but we're going to recover our key with the data protection API, and once that key is recovered, then we're going to use it to decrypt our data with AES GCM. So let's start stepping through this example. I'll enter in a message that we want to encrypt. So I'll just input here super secret message. So after we take the input from the user, we create a 32-byte random number for the AES key. Then we create our 12-byte nonce, which is what we need for AES GCM. And then we're going to encrypt our text exactly the same as what we looked at previously. We're just going to call gcmhelper.encrypt, and that gives us our result. Now if you'll remember, this returns a tuple for the ciphertext and the tag, which you can see down here. Here's our ciphertext as a byte array, and here's our tag, also as a byte array. So we've encrypted our text. Now we want to protect our key. So we're going to use our protect method and pass in the key as a byte array. And here we'll just pass in some random entropy that we're generating with the random number generator. And again, we're doing this under the current user scope. What we have now in this encrypted data here is the protected version of the AES key. So we've encrypted our data with AES and we've protected the key. And with this, maybe you can store that key somewhere in a database because it is protected now. And maybe you say we want to come back and decrypt this data. So we'll go back into our decrypt text method. Now the first thing we need to do before we can decrypt that message with AES is we need to unprotect that key. So we need to get that key back. So here we have the byte array that we pass in, which is our encrypted key, then the entropy, and again our scope, which is the current user. So here we have the byte array, which is our encrypted string, we have our optional entropy, and we have our data protection scope, which is the current user. We'll call the protected data.unprotect method, which uses that data protection API to unprotect the key. Now at this point, the key here has been unprotected. It's now the original AES key, which means that we can go ahead and decrypt it using AES GCM just like we've done previously. Now we'll call the protected data.unprotect method, which uses the data protection API to unprotect our key. So at this point, the key that we have is now unprotected. It's the original AES key, which means that we can go and decrypt our message using AES GCM just like we've done previously. So on our screen, we entered a message which we encrypted with AES, then we protected the key using the data protection API. We then unprotected the key, also using the data protection API, and then we used AES GCM to decrypt our text, which gave us the original text back, which in this case is super secret message. So the data protection API provides a really good way for us to be able to protect some data either at the local user level or at the machine level. And this is really good if you want to offer some protection to a key and then maybe store locally on a database. We're now going to look at a demo of using the RSA class, and I'll explain how to use the RSA class to create keys, and then I'll perform a simple encrypt and decrypt operation, and then next I'll show you that process again. I'll export the public and encrypted private keys and then re-import them before encrypting and decrypting. So let's take a look. We have a file here called rsahelper.cs. So in this class, it's pretty straightforward. we have a few methods. So in the constructor, we're creating an RSA class instance via the static create method. Here we're passing in 2048, which is a key size. We could pass in 1024 bits, which I wouldn't recommend because that's very small. Or we could pass in 4096. Then we have our encrypt method. This takes in a string, but then internally in this class, when we call rsa.encrypt, we then convert that string into a byte array. Now, alternatively, we could have this method take a byte array as a parameter and have that passed straight into the rsa.encrypt method. Then we have our decrypt method, and again this takes in a byte array of our data that we want to decrypt, and that just passes that into the rsa.decrypt method, which returns a byte array of our decrypted data. So as you can see, it's pretty straightforward to use. Then we have a few methods to handle the importing and exporting of key material. So the first one we have here is export private key, and for the parameters, this method takes a number of iterations, which is the number of times that our password or key is going to be encrypted. And we also take in a string as a password. So first of all, we create a PBE parameters class, then we pass in some parameters here. So we just let it know that we want to encrypt our key using AES 256-bit key in cipher block chaining mode. And we're going to use an internal hashing algorithm of SHA-256. And then we also want to pass in our number of iterations. And then on our RSA class, we call export encrypted PKCS8 private key. And then we pass in our password, which we first want to convert into a byte array. And we pass in our key params class. Now, we don't have to use a string-based password, but typically when this is used, it's done with a password. We could generate a 32-byte random number because it's effectively going to be used as an AES key. But in this example, we're going to use a password which gets converted into a byte array before the export takes place. Once we've called export encrypted PKCS8 private key, we get a byte array back, which is our encrypted and exported private key material. So our next method is import encrypted private key. So once we've encrypted it and exported that key, at some point we want to re-import that key. So we pass in a byte array of our encrypted key, and we pass in a reference to our password. And again, we call import encrypted PKCS8 private key. Our password is first encrypted into a byte array, and we pass in the information that we want to import, which is our encrypted key. And the final two methods we have is export public key, and this is really straightforward, no parameters. You just call export RSA public key, which gives you a byte array with the public key material. It doesn't need to be encrypted because it's a public key, so anyone can know about it. It's not really secret, and this can be sent to anyone. Now finally, we have a method here called import public key, where we pass in the exported public key, and it just gets imported into the RSA class. Pretty straightforward. So let's get to our form1.cs. So first of all, what we're going to do here is we're going to run through a simple scenario where we just do some simple encrypting and decrypting, and then we're going to do an example where we encrypt and decrypt, but with a key import and export as well. So first of all, what we're going to do here is we're going to run through a simple scenario where we're just going to do some simple encrypting and decrypting, and then we're going to do an example where we encrypt and decrypt, but with key export and import as well. So first of all, I'm going to give ourselves a message that we want to encrypt, and I'll just put in a super secret message again, just like we did before. So first of all, we create an instance of our new RSA class, and we store the message that we wanted to encrypt, which in this case is super secret message. Then we just call our rsa.encrypt method, passing in that text, which will give us a byte array back out, which we can see here. Here's our encrypted byte array of our message. And so next we will decrypt so that we can return that message back to the user, and we will encode that decrypted byte array back into a string, which you can see here, the decrypted message is exactly what we entered, super secret message. And so we can see that here we entered super secret message. Here's our encrypted RSA, and here is our decrypted text super secret message. And so now let's do that again, but using key export. And so I'll enter in super secret message once again, and I'll step into this method. And so here again we're creating a new instance of our RSA helper class. Then we are storing a password that we're generating here with random number generator. Then what we're going to do here is we're going to first export our private key. So we have an iteration count of 100,000 and we're passing in our password as a string. And so this will give us our encrypted private key, which you could see here again as a byte array. So that's our private key that's been encrypted. And again, we're going to give our program the message that we entered into the window as before, which in this case was super secret message. And now we're going to encrypt that message using RSA. Now we're going to create a new instance again of our RSA helper class. And then what we're going to do is we're going to import the public key and import our encrypted private key using that same password that we generated before. And then we can run through those steps to reflect that back onto the screen. And again, you could see here our encrypted message was super secret message. Here it is with RSA using key export, and here's our decrypted text. So again, very similar to what we did before, but we're just using key export, whereas the other one is a more bare bones approach. So we can remove these breakpoints and we can run through it again without debugging. And so again, I'll put in super secret message. We'll encrypt that. Here's our encrypted message using our RSA here. Here it is decrypted. Now here it is encrypted again using RSA, but with key export as well. And so you can see that RSA is a very powerful encryption and decryption algorithm. And from a usage standpoint, as a developer in .NET, it's really very easy to use. So if you just spend a bit of time to play around with the RSA class and just step through it yourself, I think you'll be able to use it quite effectively. In this demo, I'll show you how to use hybrid encryption by using RSA and AES with cipher block chaining. Now, the reason it's called hybrid encryption is because that's a term that's used when we take different cryptographic primitives and we combine them together. So first of all, let's take a look at cbchelper.cs. So this class will look very similar to what we looked at before. We have two methods, encrypt and decrypt, which takes our data to encrypt, a key, and initialization vector. Now for this example, we're keeping it simple, so we're going to be using the standard version of AES with cipher block chaining. Then we also have rsahelper.cs, which we've just looked at. So this will do our RSA encryption and decryption. Then we have a class called packethelper.cs. So as we're encrypting our session keys and encrypting data, we'll imagine that we're notionally passing this data between individuals. So in our example, that information is going to be put into this class, and this class is effectively our packet of information that's going to go between individuals. Then we have a class called hybridhelper.cs, and this is where the magic is going to happen. So first of all, we have a method here called encryptData, and this is going to take a byte array of the data that we want to encrypt, and it's going to take an instance of our RSA class. So in our encrypt method, we're going to generate a 32-byte random number, and this is going to be our session key. Then we're going to generate a 16-byte initialization vector, and we're going to copy that into an instance of the encrypt packet class. Then using AES, we're going to encrypt our message, so we pass in the message we want to encrypt, the session key, and the initialization vector. Once we've done that, we're going to use RSA to encrypt our session key, which we're also going to put into that encrypted packet. And then we will return that packet back to the caller. Then we have our decrypt data class. So here we pass in the encrypted packets. So if we imagine that this information is sent by Alice and it's getting received by Bob, Bob is going to call this decrypt data method. So we pass in the encrypted packet and an instance of our RSA class. So what the caller needs to do is it needs to recover the AES key. So using RSA, we call decrypt, and we pass in the encrypted session key. Then that will give us our decrypted session key. So that's kind of our raw, unencrypted AES key. And we call decrypt, and we're going to pass in the encrypted data that we want to decrypt, so our decrypted session key that we've just recovered, and initialization vector. And then what we can do is we want to return that decrypted data so the caller can read it. So when we run this, I can give a message that I want to encrypt. Again, I'll just go with super secret message. We'll encrypt that. And so first of all, we're going to create an instance of our RSA class. And as part of creating an RSA class, it's going to generate some keys for us. So now we want to take the message that we want to encrypt. So in this case, it's a string and it contains the text super secret message, as you can see here. And we're going to convert that into a byte array. And then we're going to pass that into our encrypt data method with the instance of the RSA class. So we generate our session key, we generate our initialization vector, and we put that into an instance of our packet. Then we call CBC helper to encrypt our data, and we put that encrypted data into our packets, and then we use RSA to encrypt that session key, which again we put into the packet. So if we look at the contents of our encrypted packet here, so we have our encrypted data, so this is what we encrypted AES with. We have our encrypted session key, which is what we encrypted using RSA, and we have our initialization vector. So now what we want to do is decrypt that data. So if you imagine that we sent our message from Alice across to Bob, now Bob is going to use the decrypted data method to read the original message. So first of all, he's going to use RSA and his private key to decrypt that session key. So here we'll get our AES key back in its original form. And then we're going to use AES to decrypt that message using that decrypted session key, which means that in our encrypted data variable here, we have the message that we want to read. So now we can reflect this all onto the screen, which we can see here. So we've got our original message, or super secret message. Then we can see the result of that after it's been decrypted, which contains the exact same string. And we could see what we had in our encrypted session key. So what we've done here is pretty cool. So we've generated a session key, we've encrypted our message, and we then used RSA and the recipient's public key to encrypt that session key, and then the recipient has used their private key to recover that session key, which I then used to decrypt the original message. In this demo, we will look at MD5, SHA-1, SHA-256, and SHA-512 in action. So first of all, let's open up hashhelper.cs. Now this has some utility code which allows us to create hashes using SHA-1, SHA-256, SHA-512, and MD5. And as you can see, for each method, there are only a few lines of code, and that really just goes to show how easy this is to do. So let's look at the very first one for our example. So for compute hash SHA-1, in this method, we take a byte array of the data that we want to hash. So say if it was a randomly generated number, that's already a byte array. So then we could just pass that in as is. Now if it's a string that we wanted to compute a hash for, then we need to convert that into a byte array first. To create our hash, we first start off by calling the static create method on the SHA-1 object, which then gives us our SHA-1 instance. And then we simply call SHA-1.computeHash whilst passing in the data that we want to hash, and then we return the result as a byte array. Now as you can see, even if we're using SHA-256 or SHA-512 or MD5, they all follow the same exact pattern. So we use the static create method to create our hashing object, and then we call computeHash. So if we look in form1.cs, we have some example code just to exercise our utility class. So what we're going to do is we're going to have two messages which each differ merely by one character, and the idea is to show you that even a minute change in a message will completely change the hash value being returned. So for example, for MD5, we're going to create a hash of the first message and then a hash of the second message so that we can compare them and see that both hashes are completely different. So let's run this example and see it in action. So I'm going to give it two messages here. I'm going to give it message to be hashed, and our second message will be the exact same, message to be hashed, but with an exclamation point at the end. So let's hash that, and we'll step in to look at the creation of an MD5 hash. So first of all, we call the static create method on the MD5 object, and then we call md5.computeHash, and we pass in that byte array of our message, which has just been converted to a byte array prior to calling this method. So if we look here, we have a variable called md5 hashed message, and this contains a byte array of our hashed message. So we can do this again with the hashing of our second message. We call encoding.utf8.getBytes to convert it into a byte array first, and we then return the results. So again, if we step into this one, we have the byte array of our message we want to hash. We call the static create method, then we call md5.computeHash, then we return our byte array. So what we can do is we can step over each of these methods, which means we've done exactly the same process, but we've repeated it for SHA-1, SHA-256, and for SHA-512, and then we can reflect these out onto the screen. So here we can see the results. Our first message is message to be hashed with no exclamation point, and our second is exactly the same but with the exclamation point, and you can see that each of the hashed message values is completely different. So you can see that a very small change in the message results in a completely different hash. And if we run this again, but if we use the exact same message, let's say we have message and message again, and we hash that, then we can see that the hashed value is exactly the same. And again, if we change it by one character, now the hash values are very different for each of the two messages. In this demo, we will use the HMAC MD5, HMAC SHA-1, HMAC SHA-256, and HMAC SHA-512 classes in .NET. So first off, let's start by looking at the hmachelper.cs file here. So here we have examples of creating HMACs for each of our different hashing algorithms. So running from top to bottom, we have compute HMAC SHA-256, compute HMAC SHA-1, compute HMAC SHA-512, and then finally at the bottom we have compute HMAC MD5. Now, computing an HMAC is a very straightforward process, and as you can see, it's only a few lines of code. But let's just focus on the one at the top here, for example, which is compute HMAC SHA-256. Now, this method takes in two parameters. We have a byte array of the data that we want to hash, which is exactly the same as what we looked at in the previous demo with hashing. So if it's a string, we want to convert it to a byte array first, and then we have our second parameter, which is a byte array of a key. Now in this case, the key is going to be a 32-byte random number that we're going to generate. So to create our HMAC, we create an instance of our HMAC SHA-256 class in .NET, and we pass in the key in the constructor, and that gives us an instance of our HMAC object. Now we simply just call hmac.computeHash, and we pass in the byte array of the data that we want to hash, and that will return us a byte array of our final hash. And as you can see, it's exactly the same for SHA-1, SHA-512, and MD5. So let's now go and look at form1.cs. So this demo looks almost identical to what we looked at previously. So we have one message that we want to create hashes for, but we're using two different keys to generate HMACs for each of our two messages. So the idea is to understand that different keys will result in entirely different HMACs, even if the message being hashed is identical. So we will generate our keys using the random number generator.getBytes method that we looked at earlier in the video, and we will create a 32-byte key. Then what we do, for each of the hashing algorithms, we create an HMAC. So if we look at the first one there, we have compute HMAC MD5. We convert our message into a byte array first, and we pass that into the method along with our key, and then we get our hashed message back. And we do the same for MD5, SHA-1, SHA-256, and SHA-512, and then we reflect those onto the screen just like we have done before. So let's go and take a look at this in action. So let's enter in a message that we want to hash. We'll just say message to hash. We'll hash that. And then we'll generate 2 example keys, and those are 32-byte random numbers. And then we're going to step into this first example of creating an MD5 HMAC. So first of all, we're getting that original message string, and we're calling encoding.utf8.getBytes to convert it into a byte array. So you can see that we're passing in the byte array of our data to be hashed, which is that string converted into a byte array. And then we have our key, which is 32 bytes that we also passed in. So then we're just going to create an instance of the HMAC MD5 class, pass in the key as the constructor parameter, and this gives us our HMAC object. Then we just call hmac.computeHash, passing in the byte array we want to hash, and then we return that hashed code. And again, we do this for each of our examples, which we can then reflect onto the screen. So here we can see the examples of those HMACs on the screen. So it's very similar to the hashing demo, except the main difference is instead of just passing in the data that we want to hash, we're also passing in a key. And what makes this significant is if a recipient or someone else wants to generate the same hash code, then they must also have the same exact key. If I have a different key, as we have here, and we generate a hash for a message, although the message is the same, the hash here will be very different. So now let's look at hybrid encryption with integrity using AES GCM mode. Now if you remember back to when we spoke about symmetric encryption, we said that AES GCM mode is a preferred way of using AES. And the AES GCM class built into .NET gives us some interesting properties. So if we go to gcmhelper.cs, we can see that the AES GCM class built into .NET is provided here, and this is all code that is part of .NET 6 and 7 and is available to anyone who wishes to use cryptography in their program projects. So one of the interesting properties here is that when we go to encrypt some data, it returns this tuple. So that tuple has the ciphertext. It also contains something called a tag. Now that tag is effectively an HMAC, but instead of us generating it ourselves, it's being returned to us by AES GCM. We are actually simplifying some of the steps because a lot of what we need is actually built into the AES GCM class itself, and that makes our lives very easy. So this class is basically the same as what we looked at in the previous examples. So the encrypt method takes the data to encrypt, it takes the byte array of our key, and it takes a 12-byte byte array, which is a nonce. Now this is conceptually similar to an initialization vector, but in the AES GCM parlance, it's called a nonce. And then we have some associated data that you can pass through if you want to. So we create a tag, 16 bytes. We create an array to store our ciphertext. We then instance the AES GCM class, passing in the key, and then we just call AES GCM.encrypt. Now conversely, when we decrypt our data, we pass in the ciphertext, the key, the nonce, and the tag, which was generated as part of the encryption process, and lastly, our optional associated data. Then we create a byte array, instance AES GCM using the key, and we call the decrypt method. Now if the data being decrypted doesn't match the tag that's being passed into it, then it will throw an exception and it will bail out at that point. So it's basically doing an HMAC check for us internally. So with the RSA helper class, we have an encrypt data and decrypt data method where we pass in the byte array of what we want to encrypt or decrypt. If you remember previously where we showed how to combine RSA and AES together so that we can use RSA to encrypt the AES session keys, it's basically the same as that, and I don't really need to go through that again. And if we look at our packethelper.cs class, it looks similar to what we had in a previous example. So we have the session key, we have the encrypted data, and we have the nonce. So instead of it being an initialization vector, it's going to be a 12-byte nonce. And then we have the tag, which is returned by the AES encryption process. So if we look at our hybridhelper.cs file, we have the encrypt data method, which again takes in a byte array of what you want to encrypt and an instance of the RSA class. So we generate our session key, which is 32 bytes. We instantiate the encrypted packet, and we generate a 12-byte nonce. Then we call the gcmhelper.encrypt method, passing in the message that we want to encrypt, the session key, and the nonce, and null for the associated data, because we're not going to be using any right now. Then it returns back to us a tuple, which contains the ciphertext and contains the tag. So we then copy that ciphertext into the encrypted data packet, and then we use RSA to encrypt the session key, which we store into the packet. So when we come to decrypt our packet of information, the process is very simple. We call RSA params.decryptData, passing in the encrypted session key, and then that decrypts the AES key for us. Then we call gcmhelper.decrypt, and that will take our encrypted data, taking the session key that we've got, and the nonce and the tag, and then it will decrypt that data and give us that back, which we will then read. So let's look at this in a demo. So again, I will enter super secret message as our message to encrypt. And so now we're going to encrypt that data. So if we pretend that we're Alice and we're getting ready to send our message to Bob, we're going to call hybridhelper.encryptData, and we're going to pass in a byte array of the text that we want to encrypt by doing utf8.getBytes, and we're going to pass in an instance of the RSA class, which contains our public key. So when we step in, it generates a random number, the session key, it creates our encrypted packet. Then we call our gcmhelper.encrypt method, passing in the byte array of the text we want to encrypt, the session key, and our 12-byte nonce. Then that returns us our ciphertext and our tag into these byte arrays, which we can store in the encrypted packet. And then using RSA, we're going to encrypt that session key and also put that in the packet. So now Alice has done her encryption process, and now she's ready to send that message over to Bob. In this line here, we'll imagine that this has now been sent across the network and Bob is in receipt of this packet of information. So first of all, he needs to decrypt that session key exactly the same as what we've done in previous examples. So using RSA, he decrypts that key using his private key, and then we call gcmhelper.decrypt, passing in our encrypted data, the decrypted session key, the nonce, the tag, and null for our associated data. Now, if any of this data has been tampered with, or the nonce has been tampered with, or the tag has been tampered with, we'll get an exception thrown at this point, because the AES GCM class in .NET is essentially doing an HMAC check here. So if we write this out to the screen, here you could see the results. So we have the message before encryption here, super secret message. It's been sent to Bob. He's decrypted everything with his session key. And then here we can see the message after decryption, super secret message, which reads exactly the same as what we input earlier. So this is a very interesting demonstration here. What the AES GCM class does is it encapsulates the HMAC process within the encryption process, and it will return that HMAC as a tag. So you kind of get both of these operations combined into one. And as you can see, that makes the coding process here a lot more straightforward to use. In this code demo, we will use the RFC2898 derive bytes class in .NET to hash passwords with different numbers of iterations, and we'll use a stopwatch object to time how long these different variations take and then display the results onto the window. So let's take a look. You'll see we have a class called RFC2898 derive bytes, and we have a static method called PBKDF2. First, we pass in our password to hash. We then pass in our salt value. In this case, it's a 32-byte random value. Then we pass in the number of rounds or iterations we want to use, and then we can specify what hashing algorithm we're going to use as well. So in this instance, we're going to use SHA-256. And that final value, 32, is the number of bytes that we want to be returned for our hash. Now, because SHA-256 returns a 32-byte hash value, we're going to put 32 as that value. But say if we're using, for example, SHA-1, which produces a 160-bit value, we would pass in 20 instead. But for now, we're going to use SHA-256, and so this value should be 32. Now PBK-DF2, this is the method that actually does the password-based key derivation function, and it's nice and straightforward, and it's just one line of code. We'll also use the stopwatch.startNew method to create our stopwatch, and the reason we're doing this is so we can illustrate how the number of rounds or iterations affects the length of time it takes to hash the passwords. So we're going to call that RFC 2898 derive bytes.pbkdf2 method multiple times, and we're going to start from 100 iterations, then we're going to use 50,000 iterations, 1 million iterations, and finally 3 million iterations. Then we'll output those timings onto the screen so you can see how long it takes. Now, I'm not going to step into this method because if I do that, then I'm going to affect the stopwatch. But what you'll notice when I run this is they will gradually take longer each time we run. Now when I input my password to hash as my password, we can see the hash, and then we can see the time to hash in milliseconds. Now each hash is different because we're generating this with a different salt each time. See random number generator .get bytes, this is our salt value, as you can see here. And so you can see with 100 iterations, the time to hash in milliseconds was 0. It took 0 milliseconds to hash 100 times. Now let's see 50,000 iterations. The time to hash in milliseconds was 25. Then we jump all the way to 1 million iterations. Now that time to hash was a lot longer, 483. Lastly, with 3 million iterations, the time to hash took 1,454 milliseconds. Now if I run this again, times might be slightly different. Yeah, okay. So for 1 million iterations, it took 485 milliseconds. For 3 million, it took 1,453. So the time to hash here depends on the computer load. But every time I run this, you can see that the time to hash, based on the number of iterations, increases dramatically. So this is very powerful because if we didn't have this algorithmic way of slowing down the iterations for the hashing process, then with a modern GPU, you could test billions of password combinations per second. Now in this example, we're only using our CPU. I'm not even using the GPU. And even so, when I click this, I went through all these iterations in only a couple of seconds. But what I want you to understand is that if your password takes 1 second to hash, or even 2 seconds to hash, then that will completely slow down the amount of passwords that you can test at a single time. And this is remarkably effective. An important function in cryptography is to ensure the non-repudiation of a sent message. This is where the receiver of a message cannot deny that the message is authentic. A digital signature is a technique used to demonstrate the authenticity of a message. A valid digital signature gives a recipient reason to believe that the message was created by a known sender such that the sender cannot deny having sent the message. And in this demo, I'll perform a simple sign and verify operation so you can see how easy it is to create a signature and then verify it. I will also demonstrate how a digital signature can fail the verification step. So let's look at our class called signaturehelper.cs. So in the constructor, we create our RSA object, and in this case, we're using a 2048-bit key. Then we have a helper method called compute-hash SHA-256. And just like we looked at earlier in the video, it allows us to create a SHA-256 hash of a piece of data that's passed into a byte array, and it returns our hash also as a byte array. So our first digital signature method is called signData. This method takes a byte array of the data we want to sign. Then what we do is we create a hash of that data. So if we pass a large block of data into the signData method, say a file, for example, first we take a hash of that data, and it's that hash that we're going to create a digital signature for. And then we call rsa.signHash, and here we pass in the hash of the data that we want to sign, which is calculated, and we'll tell it what hashing algorithm we're going to use, in this case SHA-256. Then we also pass in a padding mode. In this case, we're using PKCS1. So this just tells the sign hash method what we want to pad the end of the message with. Now once we've called that, we return a tuple. So we return the actual signature itself and also the hash of the data we want to sign. Then this final method is verify signature. So in this method, we pass in a byte array of the actual digital signature that we want to verify, and we also pass in the hash of the data that we're testing the signature on. Then very simply, we just call rsa.verifyHash. So we pass in the hash of the data to sign, we pass in the signature that was previously calculated, and again, we just tell it what hashing algorithm we're using and what padding mode to use. This method will return either true or false. So if true, the signature matches the hash, and if false, they don't match the hash. So let's look at our code here. We start off with the message that we want to sign. In this case, it's just input from the user. However, signatures are often used for a much larger document, such as a file. Now, we want to make sure that our message is converted into a byte array. So again, we use the encoding class and we call utf8.getBytes to turn that into a byte array. Then we create an instance of our signature helper class. And then we sign our data by passing that document into the signed data method, and that will return us that signature variable, which if you remember is a tuple. So it contains a signature and the hash of the data that we've passed in. Now straight away we call verify signature and we pass in the signature and the hash, and that will return either true or false. And lastly, we will reflect that result onto the screen. So let's run this and take a look. So first of all, I'll enter in my message. So I'll just say message to sign. We'll sign that. So we turn that message into a byte array, and we're going to create an instance of our signature helper method, and we're then going to sign our data. So we create a hash of the data that we've passed in, and then we call the rsa.signHash, and we provide it that hash that we've just created, and then we return that hash and the signature back to our caller. So now we want to verify that signature. So here we've provided the signature and the hash of the data, and we call verify hash and return. Now when we continue, we can see that the value is true, so the signature is valid. And here is the signature of our message. So what I want to do now is run this again, but once we've created our digital signature, we're then going to pretend to be someone malicious, and we're going to tamper with that data and see what happens. So again, I'll pass in our message to sign. So again, we have our message, we create the new digital signature class, and I'm going to sign that message. So here we can see that item 1 is the digital signature and item 2 is the hash of that data. Now I'm going to come in here and I'm going to be malicious and I'll change an item in that hash. So let's say I change this from 25 to 30, and we'll continue this and see what happens. So I've been malicious and I've intercepted the message, and so if we look at the result, it's now false and the signature is invalid. So the reason it's invalid is because I've deliberately tampered with the hash. Now we could have had the same result if I deliberately tampered with, say, the signature as well, but because the hash doesn't match that signature, it's going to return false. In this demo, I'll show you how to add a digital signature into our existing code. I'll then show you how to verify the digital signature for the recipients of the data. So let's take a look. The majority of what's in this project is identical to what we've looked at before, so we're not going to spend too much time going over it again. We have our RSA helper class with our encrypt and decrypt methods, but what we've added additionally is a signature helper class. So we have our sign data method where we pass in a hash of the data we want to sign, and we then create that signature. Next, we have a verify signature method, very similar to the ones we've looked at previously. Then in our packet helper class, this is almost identical to what we've looked at before. Now we have this thing called a tag, and the tag is pretty much the same as an HMAC. but the tag isn't the exact same format as an HMAC that the digital signature is expecting. So we're going to have to calculate a separate HMAC, which is a bit of an extra step, but it's something we have to do. We also have an additional signature member at the bottom of the class. So if we look in hybridhelper.cs, in our encrypt data method, we pass in a byte array of the data we want to encrypt. We pass in an instance of our RSA helper class, and we also pass in an instance of our signature helper class. So first of all, we generate our session key as a 32-byte random number. We create our encrypted packet, and we generate an initialization vector. But remember, in GCM mode, we call the initialization member a nonce, and it's 12 bytes instead of 16. So then we encrypt our data using the session key and the nonce using AES GCM mode, and that gives us back the ciphertext and a tag, which we both store into the encrypted packet. Next, we encrypt our session key using RSA and store that in our packet. Then we create an HMAC of the encrypted data and the initialization vector combined, and we store that into our packet. Now, because we need an HMAC for the digital signature process, the actual tag returned to us by AES GCM isn't the correct format. So we need to create a new digital signature again, and it's going to use the encrypted data plus the initialization vector in an HMAC, and that HMAC is created using the unencrypted session key. So once we've done that and stored it in our packet, we then create our digital signature, and that signature is created on a hash. But we happen to have a hash because we've just generated an HMAC, so that's the hash we're going to use. And to decrypt our data, we have our decrypt data method. So here we pass in a copy of that packet, the RSA helper class, and the signature helper class. First, we decrypt the session key using RSA. We then recalculate the HMAC using the session key, and that HMAC is taken of a combination of the encrypted data and initialization vector. We compare that HMAC that we've just calculated to the one that was sent in the packet. If they match, we can proceed because we're happy that the file hasn't been tampered with or corrupted. If they don't match, then we throw a cryptographic exception and abort. So if you wanted to compare two byte arrays to check whether they're the same or not, typically what you do is you'd iterate through both of the arrays and you check each array at its increased position. And if for any reason they don't match, we just abort at that point and return false and say they don't match. Now that's a more efficient way of doing it, but being security, doing it that way is actually a bit of a problem because it means that the time that the method takes to run could be different for different byte arrays, and this can lead to what's called a timing attack being done against the code. So what we're doing instead, we have this method here called compare. Now what this does is no matter whether the arrays are the same or different in any way, they always take the same amount of time to run. So for example, if we had an array that was 10 elements long and the arrays differed at the second element, instead of aborting at the second element, we would run through the entire 10 elements regardless and then return the result whether they are the same or not, which means that no matter what's in those arrays, they always take the same amount of time to check. And this is what we're going to do for our program here. So when we compare the byte arrays, we're making sure that it takes a constant time to run through the byte arrays. So let's run this. And once again, we will use super secret message as the message we want to encrypt. We store the message, we create the RSA class, we create the signature helper class, and we'll step into our encryption method. So here we create the session key, we create the nonce, which is 12 bytes. We encrypt our data using AES GCM, and we store the encrypted data into our packets along with the tag. We encrypt our session key with RSA, and then we calculate a new version of the HMAC because, again, we can't use the tag for the digital signature process, so we need a new HMAC. So this HMAC is a hash of the encrypted data and the initialization vector. We then create our digital signature and return. So now we'll assume that Alice has created a message message, and it's now being sent across to Bob, and so now Bob has this message. So he's going to go through the decryption process in order to read it. The first thing he does is he recovers the session key. He then uses that session key to recalculate the HMAC, which is a combination of the encrypted data and the initialization vector. He compares his new HMAC to the one that was sent to him. If it matches, we carry on. We then pass in the digital signature and that HMAC into our verify signature method. In this case, we can see it returns true, and we then decrypt our data using AES-GCM, which means Bob can now read the message. So again, let's reflect that onto the screen like we've done before. So as you can see, here's our encrypted data, which is simply this message but encrypted. You can see here's our encrypted session key, and here is our signature. And after running through this whole process, we decrypted the text, and now it returns super secret message, which is exactly the same as what we entered before. So let's see what would happen if we attempted to be malicious and try to corrupt this data in some way. We'll go execute this. Again, we'll enter super secret message, encrypt that. So let's run through this. So here, let us tinker with our signature HMAC. So I'll change this from 71 to, let's say, 90, and let's see what happens if, say, a malicious actor decides to mess around with the signature in some way. Now here you could see we received a message box. HMAC for decryption does not match encrypted packet. So here we can see what happens when the HMAC does not match and how we can handle this with exceptions. Essentially, this project here that I've just ran through is really just a culmination of everything that we have learned previously. So we learned how to use RSA, we learned how to use signatures, we learned how to use hybrid encryption, we learned how to use AES-GCM, and this whole program combines all this into what we can see here, which is essentially, I guess you could think of it as a hello world for cryptography in C# with .NET 6. So the main security requirements that we wanted to solve were confidentiality, integrity, non-repudiation, and authentication. Confidentiality is what we traditionally associate with cryptography. This is where you take a message or some other data and encrypt it to make the original data completely unreadable. We looked at two solutions for confidentiality: symmetric encryption with AES and asymmetric encryption with RSA. The second type of security operation was integrity. In information security, data integrity means maintaining and assuring the accuracy and consistency of data over its entire lifetime. This means that data cannot be modified in an unauthorized or undetectable manner. We looked at various hashing algorithms such as MD5, SHA-1, SHA-256, and SHA-512. The third type of security operation was non-repudiation. Non-repudiation is the assurance that someone cannot deny something. Typically, non-repudiation refers to the ability to ensure that a party to a contract or communication cannot deny the authenticity of their signature on a document or the sending of a message that originated with them. Non-repudiation and digital signatures are very much like a physical contract in real life. So for example, imagine you're taking out a bank loan. You go to the bank and you sign a contract, but you may also have someone witness the contract. What this means is that later down the line, if the original contract was, say, for $10,000, but then you try to say, well, actually that contract was for $5,000, you can't refute what was on the contract because A, you signed it, and B, you had someone witness this. And that's exactly what non-repudiation tries to achieve, but in the digital realm. The fourth and final security operation was that of authentication. Authentication is where you can assure that only the correct person carries out an action. We explored the use of hash message authentication codes, or HMACs, as a way to get authentication. And they're really the same as hashes, but they also use a key as part of the hashing process. This means to recalculate the same hash, you also need the same key, hence the authentication aspect.